Hello guys, today I'm showing you an iris project for machine learning. It's a classification model, of course using supervised method. I'm using Pandas, NumPy, Matplotlib, Seaborn and SkLearn. Also be using linear regression as the algorithm for training the model. Also be training these metrics, the accuracy score classification, confusion matrix, F1 score. And so I'm using this Jupyter Lab. This Jupyter Lab. The reason why I like using Jupyter Lab is because it's more advanced and it has this better user interface than the older version of it, that is the Jupyter Notebook. So I started importing this. I've imported the Pandas and NumPy. Pandas is crucial for data analysis, and this one is also used for numerical operations and other maybe in arrays and all that data types. These are for visualization. Seaborn is better for visualization, especially it's an advanced way of visualizing data than Matplotlib. So then there is the SkLearn. SkLearn is what I'm using to train the model and test the accuracy score and these other metrics. And of course, I can use SkLearn to import this algorithm, that is the logistic regression. Okay, so yeah, after loading them, the libraries, I then load the dataset. I'm using Pandas to load the dataset here using the Seaborn load dataset iris, the iris head. The reason why I'm loading dataset using this function is because of the data type that I'm using here, and also the method of loading the dataset. This is a Pandas data frame. You can check that maybe by adding another cell down here, and maybe can check type. Here is this. You can check the Pandas data frame. So, and this is the data. These are the columns. It has 5 columns, but literally I'm using these for numeric columns to train the model. The sepal length, the sepal width, the petal length, and then the petal length. These are the species, that is the setosa, vesicola, and the other one is the Virginica. So the setosa is the first species to show. That's why it's showing this. Also, the iris head shows the first 5 rows. Although you can customize this maybe by specifying the number of rows you want to show. Maybe you can put them as 50. So you can run this and you can do the 50 rows. You can see the first 50 are still setosa. Maybe if you can check this on the second one, you can see the second one is vesicola. That is from the 51th row. This is index 50 here. But if you check maybe the 100th, you see this issues with the vesicola, and maybe check about the last one. I think is 149. That one will show you the Virginica. That, and so we don't need that. I don't want. So this is the iris information. This is the information of this data, and you can get it from here. This is the class. It's a Pandas data frame to the range index, so it's 150 entries, just 149. The data columns are 5. These are the number of rows, the 150, and 0 to, you can see they are displayed here, and they are float, that is the decimals. So the string, the string is not the species. Can bring this back to a little. So the species is the string, so it has the string attribute here. There are floats. This is the memory usage, that is the size of the dataset, 6 kilobytes. Data shape, this is 150 rows by 5 columns. You can imagine it as a matrix. And so the columns, these are the present columns. I already checked them up there. This is the data type of the species, the string. Now here we are using the areas describe attribute to visualize the statistics of the data. This is the count, this is the number of rows per each column. So this is quite crucial, especially when you're working on you are analyzing data and you want to check if there are empty rows. You can use that one with Pandas with a null function. You can check. You can also use this. Maybe if you had 149 here, we will know the petal length as an empty row. This is the mean score. You won't know how to calculate the mean score, the average, that is the summation of all frequencies divided by the count of the frequency. This is the standard deviation. I'm not going to do much on the statistics here in this video. Now this is the minimum value, that is the minimum. This is the minimum recorded value of the sepal length, recorded of the sepal wing and all that. 25% is the lower quartile. It's also mathematical attribute, especially when you're checking for outliers. These values are quite crucial. This is the median, or maybe the second quartile. This is the third quartile, and so that. And this is the maximum value of the data set. This 7.9 is the longest sepal length recorded and all that. Maybe 2.5 is the longest petal length recorded. Then this is the iris species value counts. This counts the number of value in each row. Setosa has 50 rows. Physical has 50 rows. Eugenic has 50 rows. That's giving us a total of 150 rows in each of them. And also you can check the data type here. Data type, it's an integer, that is for this. So you have used Seaborn to visualize this data using the EU. Is this why I like how Seaborn was it assigns different colors to this. I didn't have to assign this manually, but it does that automatically. This is the EU. It's the EU. Can see also there is this beautiful key on the data, and also you can visualize them. You can check this the sepal length here with respect to the sepal length, the sepal wings with respect to the sepal length, the petal length, and all that. You can also check the distribution of each data. This is quite crucial, especially if you are doing data analysis. I'm not going to do deep on that. This is a correlation between numeric values. I'm using heat map. Also, I'm using a Seaborn to plot this data, to plot the heat map. But I'm not going to do much deep on this. It is not so much crucial, especially for machine learning, and unless we are doing much on data analysis and you want to clean the data and you want to understand the relationship between each data column and all that. So yeah, this is a histogram. I think this is the most crucial distribution of them. especially if you're doing if you want to avoid overfitting of the data. I think I'll do this in the second video of maybe how the distribution of each data affects each other, maybe whether it's whether we check histogram, how the data is distributed in the histogram, whether there is any kind of biasness on it. It's quite crucial. And so I'll do this in the second video. I've been using Matplotlib for the histograms and all that. The PLT dot subtitle feature distribution. Here this is a subtitle. Now the show function is common for both the Matplotlib and Seaborn. I think you have realized that. So for this, so now this is where I'm training the model, and yeah, this part I'm specifying the data for maybe the x and the y attributes. With the x is equals to reduce.drop species, that is I'm dropping the non-integer value, and yeah, I'm dropping the non-integer value. This is the species value, which is a string. Of course, I wouldn't be requiring that. And also the y now, this is the y value. That's when I'm using the species to predict the outcome of each data. Now this is a target column. You can think of it as maybe a mathematical function. I think I should show that. Maybe you can think of it as something like you can think of it maybe as an equation of a line. You can think of it as this way, and so this is the target value, this is the y function, this is what we are looking for, this is what the machine will predict. Now the m, this is the weight that the machine will, yeah, this is the model, the function of the model. This is what it defines. The m, that is the weight, the x is the x input that we are adding, and c is the bias. This is kind of a constant, it's called a bias. So yes, when we are training the data, the 80% and the 20% training. So x train, x test, x train. This is simply that we are using 80% of the total data to train and 20% of it for testing. You can change that one here. I think I had already changed. This should be 2. You can think of it as 2 divided by 100. Okay, 20. The 20% divided by 100. That's how you're getting the 0.2. You can run this and you can say I'm using 120 columns for training, and the 120 rows for training, and that column, that rows for testing. The 4 is the number of columns. So this is a model. I'm using logistic regression. You can think logistic regression is used for classification. Yeah, and it uses the logistic sigmoid function to convert the numeric values into probabilities between 0 and 1. And this is the model dot fit x train and y train. This is now where most of the training appears, and it fits the data. You can think of it now as it assigns the weights to the model, and this is a max iteration for automation. This is the model will iterate at least 200 times, or maybe it will iterate until the data converges. I'll deep dive into that in the second video. So this is logistic. There's some data shown here. Maybe I'll also go deeper into each one of these later in the next video. Okay, and this now is the prediction. See the prediction of the y value. You can see predicting the species of which we of which this is the prediction of each species. You can see the scores at also unique. This doesn't make a lot of sense here. This is the number of predictions, and see, yeah, you can say this twitch number, maybe 13 or whatever. You can. These are now the metrics. This is the accuracy score. Deep dive. I'll dive this one to the next video. Maybe how we calculate the accuracy mathematically, or maybe we do the confusion matrix, how we do the F1 score and all that. The accuracy score of 1 means that the model scored 100% on this, and this is now the confusion matrix. I'm also going to do a deep video for this. So now this is here, and together with this the F1 score, the recall, and the precision, so the support, and also maybe an overfitting. I'll do a video for that. I think I should end this one here. So thank you for watching. Maybe you can comment on what I should maybe emphasize on next time, and maybe what I should do on the next time. Okay, thank you guys.